Lesson 34, Markov property. Today we're going to talk about the MM1Q. If you haven't yet checked out the R notebook, I would probably do that one first. That is important to understand because we're going to use that code tomorrow whenever we start talking about, or whenever we start doing our simulations. So the purpose of this class is to derive the analytic queuing metrics so that we can use these metrics in order to compare to our simulation so we can validate our simulation before we start making it even more difficult than just an MM1. So that's the idea behind it. So in order to understand some of these queuing metrics, what you're going to have to do is get a hold to the infinite sums. And this is just a real quick reminder of what infinite sums are. So of course I'll do an example here. So we'll start off with an example. We'll just do 1/2. So we're going to let I is equal to 0 to infinity. So we're going to add an infinite number of these guys to the ith power. So that'll be basically just 1/2 to the 0, 1/2 to the 1. So we'll just keep adding that sucker all the way to infinity. The trick here is to, and we'll use this trick a couple of times during this video. We'll let this partial sum be 1/2 to the 0 plus 1/2 all the way up until we get to the nth power. So we get to the nth power, and then the trick really is to multiply by whatever the fraction is inside here, multiply it by Sn by that one, and we end up getting 1/2 to the first plus 1/2 to the second. Here, let me put my parentheses around there. All the way to 1/2 to the n plus 1. So we get an extra 1/2 on each one of those terms. And then you simply, the way I like to do it is just draw a line here and go, I'm going to subtract the left-hand side. So the left-hand side of the equal sign is Sn minus 1/2 Sn, right? So that's just this top part here. Let me bring it over. This top part, Sn minus 1/2 times Sn. So that gives us the left-hand side of the equation. And the right-hand side of the equation, because we did what we did, it simplifies. So 1/2 to the 0 stays, but this one will cancel out with that one because these are a bunch of minuses. So it'll be minus here, minus there, and so this guy cancels with that one, and the one after that one cancels with that one, and this one cancels with the one before that, and so really it only leaves us with two terms left: 1/2 to the 0 minus 1/2 to the n plus 1. So now we're going to just solve for Sn. So if we solve for Sn, we get Sn 1 minus 1/2, because I took an Sn out of the left-hand side of each one of those terms. And we get 1/2 to the 0 is just 1 minus 1 over 2, or 1/2 to the n plus 1. And I get Sn is 1 minus 1/2 to the n plus 1, all divided by 1 minus 1/2. And I'm going to leave it looking like that just for a second. So that we didn't ask for a partial sum, we asked for an infinite sum. So that's why we now need to take this partial sum and turn it into an infinite sum, but just by taking the limit. So if we take the limit of this partial sum Sn to the nth term, if you will, and I'm going to let that go all the way to infinity. What that allows me to do is take this fraction here, 1 minus 1/2 to the n plus 1, and so that is the part that's going to infinity, and then we still have 1 minus 1/2 here. And so if the thing that we're summing and taking to powers here, in other words, it's 1/2. If that, whatever that's in there, as long as that's less than 1, then we know if I take that sucker to infinity, then it's going to go to 0. In other words, I take a number that's between 0 and 1 to infinity, it goes to 0. So so this goes to 1 over 1 minus 1/2, which is equal to 2. But I want to leave it in this form just for a second. because now we're going to come back over and maybe solve a more general problem. So the more general problem would be I is equal to 0 to infinity, and I'm gonna call it rho. So as long as rho, and I put a parenthesis around it, for rho between 0 and 1, as long as that's true, then you just take the same sort of steps that we took over here for rho, and we would get this would be equal to 1 over 1 minus rho. So, for example, if rho is equal to 1/2, then it's just 1 over 1 minus 1/2, which ends up being 2, which is exactly what we suspect. But if you put 3/4 in there, then it would be 1 over 1 minus 3/4. I believe it's 4, whatever. Just do the math on that and figure it out. So that answers that question. So the question here that we're trying to answer is, what is the sum from I is equal to 0 to infinity of rho to the ith power that is equal to 1 over 1 minus rho, as long as rho, so as long as rho is between 0 and 1. And that's in general for these infinite Q's, these infinite lines, in other words. That's if you don't have that, then your line's going to blow up. There's going to be an infinite number of people kind of jumping in your line. So you had to have that. Sort of has to be the solution. The next question that we want to answer is, what happens when, so say we started at 1 and goes to infinity of rho. So that would be another question that we need to answer, and we're going to use the same sort of trick in order to answer this one. Actually, no, we're gonna do another little trick in order to do this one. So all I'm going to do is multiply by p to the 1 times p to the negative 1. That's equal to, I'm sorry, not p, rho. Rho to the 1 times rho to the negative 1 is equal to, if you remember your multiplying bases with two numbers that have the same base, what you do is you add the powers. So if we add the power there, we would get rho to the 0, which we know is 1. So if I just multiply by 1, so that multiplying by this, or bringing these two terms in, is the same thing as multiply by 1, and we know we can always do that. So I'm going to bring a rho to the first power outside the summation sign, and then I'm going to bring, here, let me move this. So I'm gonna bring it down a little bit. I'm gonna bring a rho to the first power outside the summation sign, and I'm still gonna go from, oops, not 0 but 1. I'm gonna go from 1 to infinity, and then I'm gonna have rho negative 1 inside my summation sign, and then I'm gonna have rho to the I, and that's going to end up being rho summation from I is equal to 1 to infinity still. And then this will be rho to the, again, adding the powers, I minus 1, ends up being I minus 1. And that will end up being, oh, so now what we're going to do is, I'm going to let this I minus 1, I'm going to do a change of variable, so I'm going to let that be j. So j is equal to I minus 1. So this will be rho j is equal to, well, just put in I into this equation, and you get 1 minus 1, which is 0. So j is going to start at 0. It's going to go to infinity, and it's going to be rho to the j power. Well, we just found out what that's equal to. We know this already, because that's our first little sort of result that we got up there. We know this is 1 over 1 minus rho. So because of that, I can just simply say that the sum from I is equal to 1 to infinity rho of I is equal to rho over 1 minus rho. And there might be an easier way of doing that, but that's the way that I did it, just to show you or to remind you what that sucker is equal to. So we have this result. I put a little star by it, and we have this result, and we put a star by it. We're going to need both of those here in a few minutes. So our next thing that we want to talk about, so that's just a review of infinite sums. So the next thing we talk about are these things called steady state probabilities. And if we remember, because we're talking about probabilities, that let's see, P0 plus P1 plus P2 plus dot 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 plus an infinite number of these states, if you will. If we added up all of those probabilities, they better all sum up to 1. And we remember this from our balance equations. So our balance equations and a little bit of algebra get us this, that P0, and there's a relationship between P0 and all the other probabilities. It's just lambda over mu times P0. And I'm not sure, have I talked about lambda and mu yet? Maybe not. So let's go ahead and define what lambda and mu are. Lambda was the arrival rate, and mu was the departure rate, or we'll call it service rate today. And this was still a birth-death process, so that would be 1, which looks like the rate at which I go from 0 to 1 is lambda. The rate at which I go from 1 to 0 would be mu. And that's true for every single one of these. But this sucker goes on forever, right? So it would never, in this particular case, what we're talking about today, this MM1Q, doesn't have a limit to the number of states that it can have. So that's the idea. Okay, so let's keep writing these just for a second, or just for a couple more. Now that wouldn't make any sense. So it was squared and so on and so forth, all the way till you get to the ith one, and that would be lambda over, and I'm going to get tired of writing lambda over mu. So I'm going to call this thing rho is equal to lambda over mu. So just simply take the arrival rate, divide by the service rate, and we're going to call that rho. And no other reason than I just get tired of writing lambda over mu, and I can just write rho very quickly. And I'll probably call it p, but I mean rho. So now we want to go back and see if we can derive or find a value for P0. So that's the idea now, is we just want to come up with a value for P0. So start off with, let's just write out a couple of these. So P0, we don't know what P0 is, so we got P0, and then I can turn P1 into terms of P0. I just said we were going to use rho, so I'm going to go ahead and start writing rho now. P0 plus rho squared, P0 plus rho to the third P0, right? So this one would be P1, this would be P2, this would be P3, plus dot dot dot, and if we add all the suckers up, we better get equal 1. Okay, so now what I want to do is take this and turn it into a summation sign. So if I were to write this in terms of I is equal to 0 to infinity, we would have rho to the ith power times P0. And since P0 doesn't have an I term in it, I can bring it outside the summation sign. But we still know that sucker is equal to 1, so I can bring P0 out. It doesn't have an I term in it. So I is equal to 0 to infinity of rho sub I. And again, we have to assume that your arrival rate is less than your is less than your service rate, so that rho is equal to lambda over mu is less than 1. I want that to be less than 1, and if that's true, then we know the answer to this. This will be P0 1 over 1 minus rho is equal to 1. So all I did was take this and the result that we already talked about and put that in for for that summation sign. And now what we can do is we can simply just solve for P0. So if this were the case, then P0 must be, multiply both sides by 1 minus rho, and we just get 1 minus rho. And we can use that and substitute into here, and we get any state I that we're looking for. We can find a steady state probability simply by taking rho to the ith power and multiplying it by 1 minus rho. So this is our result for any steady state probability. And oh, by the way, P0 as well, right? So we know what so once you know P0 is equal to that, then we're just simply substituting them back into these, and we're putting rho in for lambda over mu, and you get this. So I can put a star by that equation as well. So let's go down to our next metric, if you will. So let me put a little bit of space in here. Our next metric is, or I shouldn't even say our next metric. Really, this is the first metric that we talked about. In general, when people are doing a queuing system, they want to know a couple things. One is, and let me just sort of highlight it here. One is the average number of customers in the system, right? Because if your mu and lambdas aren't, if they're too close together, you're going to get a lot of people waiting. If matter of fact, if lambda is too big, you could get an infinite number of people, as we just discussed a few minutes ago. Or if you could look at the math, back at the math equations, you can see. And another thing that people are concerned with is the average amount of time that it takes someone to go through the system. So those are two things that we need to derive, or at least I want to derive a formula for, in order to be able to validate our simulation tomorrow. So the first piece here is the average number of customers. So if I know this, so if I know my states, remember how we define states. Our states are the number of customers in the system. So I can have 0, I can have 1, I can have 2, I can have 3, ... I can have I. So I know that I can have a certain number of people in the system, and that's what our state represents. The number, the x of t is equal to the number of people in the system. And I know that I can get the probability that x sub t in the long-term probability, so steady state probability, is in state I. All right, actually, we'll write it in terms, probability x of t is in state. Then we know this will be P0, this would be P1, this would be P2, ... And we have a formula for this now. So the thing that we just calculated above was P to the ith power. So for the 0th one, it's just 1 minus P. 1 minus, I told you I was going to call it P. 1 minus rho. This one would be rho to the first, 1 minus rho. Rho to the second, 1 minus rho. And if you go to the ith power, Pi is equal to rho to the ith, 1 minus rho. So now let's use this in order to figure out what our average number of customers in the system. So how could I use this? Well, it would be the probability that I'm in state 0 times 0. So again, go back and remember what the expected value is. If you're given a distribution and you're given the support for that distribution, all you're going to do is take, so L would be the number of people times the probability of being in that state, plus the number of people times the probability of having 1, plus 2 times the probability of having 2, and so on and so forth, all the way to infinity. So this would be, if we want to rewrite it in terms of a summation sign, I goes from 0 to infinity of I times P sub I, which is equal to, we're just going to use some of the results that we've already talked about, so that I would stay there, and I'm going to use this, bring it down, row I, 1 minus row. So what we can do is bring this outside. It does not have an I. So we can bring it outside our summation sign. So 1 minus row, summation from I is equal to 0 to infinity of, let's see what's left, I times row I. So 1 minus row comes out, and we're left with that. So the deal is, and I'm going to do all of this in red here, if I knew this, then I'd be done. And I'm going to call this S. I'm going to call this sum. I don't know what it is, but let's use our little tricks in our that we've used before in order to try to figure out what that sucker is. So we know, so let's go ahead and start writing out some of these terms. So S is equal to, so I put in 0, I get 0 times row to the 0. Put in 1, you get 1 times, so 1 times row to the 1. And it looks like this is what it comes out to be. Third, I'm gonna do a bunch of, maybe not a bunch, maybe I'll stop there. But we know that that's what that sum looks like. And if I knew what that was, I'd be done. I could just type it in or write it in there, and we'd be money. But let's use one of the tricks that we've learned before, where we multiply by row. So I'm going to multiply every term here by row. In that case, it would be 0 times row to the 1. And I'm writing that out. I know that's 0, but I'm still writing it out because I just needed to set the pattern. And this would be 1 times row squared plus 2 times row third plus 3 times row to the 4th, 4 times row to the 5th, and so on and so forth. And now remember the trick. We just take this, draw a line, subtract, and then, so it would be S minus row S. Right, so that's the left-hand side of my equal sign. And my right-hand side just comes out to something I think is a little neat, but we'll see. So first of all, this one is just 0. I'm not going to worry about it, but I do want to worry about the rows that have a 1 power. So I'm going to take those, and because this is a positive and the 1 in the bottom is a negative, I'm going to subtract. I'm going to call it row to the 1. I'm going to get a different color, and I'm going to just note that that has a row to the 2nd power, and this one also has a row to the 2nd power. So again, the 2 is positive and the 1 is negative, and we write the 2nd power. And let me get, I don't want to get red because that's what we started off with. So green, and you can see the pattern here. So it's 3 minus 2, row to the 3rd, and then I'll just get back at white, and so this just becomes the pattern. So let's figure out what to do with those. So we get S, so that's what we're looking for, 1 minus row, and that's equal to, well, this is 1, this is 1, this is 1, and then every single one of those will be 1. So what we're talking about is just row to the 1st, plus row to the 2nd, plus row to the 3rd, plus dot, dot, dot. It's going to just, that's the pattern. That's what we're going to end up doing. So let's write a summation sign for that. So it's I is equal to, it's like it starts off at 1 and it goes to infinity of row to the I. It just so happens that we figured out what that one is already. So let's go back up and just recall it. Let me get a purple out here. Okay, yeah, this was it right here. So this was what we already figured out. So if I'm starting at 1 instead of 0, then it's row over 1 minus row. So let's go back down and then write row over 1 minus row in for that. So this results in S 1 minus row is equal to row over 1 minus row. So we know that S must be equal to, so S must be equal to row over 1 minus row squared. All right. So now we can take this S and substitute it back into here and actually get the result that we're looking for. So here, let me put a little bit of space in here. I don't think I have quite enough yet. Put a little bit more. So we get L is equal to, so I'm just 1 minus rho, and that summation sign, that S, which is equal to 1 minus rho times rho over 1 minus rho quantity squared. And then this one cancels out with one of those, and we're just left with rho over 1 minus rho. Now this will work. This formula is not that big a deal. It's not hard. But the one that you'll probably see if you're sort of reading in another book is that what they do is they end up taking that rho is equal to lambda over mu and substituting that back in. So you get lambda over mu. So I'm going to put an equal sign there, lambda over mu, and then 1 minus lambda over mu. And then if we want to simplify this, we multiply by 1. So we know we can multiply by 1. And the one that we want to multiply by is the one that will simplify this a little bit for us. So mu over mu is the same thing as multiplying by 1. And if you multiply by that, the top, these mu's cancel off. It just leaves you with lambda in the numerator. And then the denominator, 1 times mu, leaves me mu here. And then lambda over mu again times mu gives the mu's cancel off, and it just minus lambda. And so this is what you'll see most of the time. If you're talking, and L is the letter that people use. I'm not real sure why off the top of my head right now. But L is the letter that most books use. If you're going to check this out, is the average number of customers in a system, and that is lambda over mu minus lambda. It probably has something to do with the person's last name, Little, who did a lot of research on this, but I'm not sure. I'm not gonna promise you that's the reason why it's called L in most books. Okay, so that's the thing that we want to observe there. So if I know lambda and mu, then I can quickly tell you the average number of customers in a system for this MM1 that does not have a limit to the number of states that you can be in. The next thing that we want to talk about is a little bit, it's not a proof, and I'm not going to do any a lot of hard mathematics on this. What we're going to do, though, is we will sort of talk through the reason why this next equation is true. And so let's redefine, or let's relist out here what L is. So L, again, is the average number of customers in the system. And lambda, all right, so in case you forgot, a lambda is the arrival rate. So arrival rate of customers to the system. And let's just for a second talk about this lambda, this idea of lambda. I'm going to use another color here and give an example. Let's just say that lambda is equal to 4 customers per hour. That's generally a pretty good time to use. How many would I expect? So if my rate at which customers arrive are 4 per hour, how many would I expect if I were looking at a 10-hour period? So it's not a hard thing to think of. So over that 10-hour period, I would expect just your rate times your time, which would be 4 times 10. Or I would expect 40. So if time equals 10 hours, then we expect, and I put that in quotation marks there, we expect about, I'm using about because we know it's a stochastic process, about 40 customers. if it were only a 2-hour time period, so let's say a 2-hour that we're interested in, then we would expect 2 times 4, which we'd expect on average 8 arrivals. Okay, so really, I mean, to sum it up, once you're given the rate, you multiply that by the time to give you the expected number of arrivals. And hopefully that makes sense. Poisson process, we talked about this. I mean, generally that's what you're talking about here, Poisson process, because we're saying these things are exponential inter-arrival times or service times. So in general, that hopefully that makes sense to you. And the last thing I need to define is the thing that we define right above here, right? So I already did it in typed letters, but I'm just going to let this be the average amount of time in the system. Okay, so let's suppose that customer A, so at equilibrium, suppose customer A enters the system. And takes, on average, W time to go through. Okay, so let's just write this out. So customer A arrives to the system. And what we're saying, and I don't know how big, it doesn't really matter how large W is. So this is W amount of time on average. And then A departs. The question is, how many folks have, so remember this is a first, I guess I need to write that too. It's a first in and first out system, first out queue. And if that's the case, then everyone who arrives after A is going to have to wait until A is out before they can start being serviced. But the question is, how many people? So how many people would arrive during, and we'll use hours. Again, this could be any time period. We'll just say hours because of our example above. How many people or customers or whatever you want to call it, forklifts, would arrive during the time that it takes customer A to go through? And remember, the amount of time is on average W. So again, up here we had hard times for I had 2 hours and I had 10 hours. But in this case, we have W. So lambda W would give me the number of the expected, that's what I should say, the expected number of arrivals. And when that customer A departs, I mean, again, A I used as maybe arbitrary customer, but when that customer A departs, he's leaving lambda times W customers in the system. So on average, we expect to have L customers. Okay, so this leads to the equation, and this is the point what I was talking about. It's called the Little's queuing formula, and that's probably what this L stands for, but L is equal to lambda times W is Little's queuing formula, I believe, formula that relates the L, lambda, and W. And that's the idea behind it. That's certainly not a proof, but I at least wanted to give you maybe some reasoning behind that and just talk it through. Okay, so if that's the case, then we can very easily say, well, that means that W, divide by lambda, so L over lambda, and we already know L, so it's equal to, I don't remember off the top of my head, I have to read the lambda over mu minus lambda. So 1 over lambda, which is that part on the bottom, times L, which is lambda over mu minus lambda, which would be equal to 1 over mu minus lambda. So W is equal to 1 over mu minus lambda. And I'm going to put a box around that one, and we will be done, at least for the derivations and whatnot. What I do want to do is make sure that everyone remembers to go, because we haven't done one in a long time, goes to the R notebook. So let me show you the R notebook just real quick. So the R notebook is out there on our course website. Let me just go there. Remember, it's in R notebooks. And in here, you can see lesson 34 QMM1. So what this does is it sort of takes you through, if you read and then follow along, it takes you through the reasoning behind the program, right? So I set it up here, and then I created this thing called record time, and there's a reason why we create this thing called record time. And it's all about, like, I don't know how many states there's going to be, so I have to have this function that will either increase the amount of time, or it will create a new state and have that be my amount of time. And then you can it just sort of goes through a couple examples, and then I just slowly build our queue function for this MM1 server. And then I validate it. I always try to validate the code to make sure that it's all making sense. And then we set a seed here. So if you set the seed and you run it, you get the same numbers. And then I just sort of talk you through validating both of the system statistics that are coming out and the customer statistics that are coming out. Anyway, it would be nice if you understood the code, because we're going to end up using it in class tomorrow. That is all that I have for this lesson. So I invite you to ask questions tomorrow if you don't understand. That's all I got. See you tomorrow.